So the final piece of the puzzle for this discussion of parallel streams internals, we'll talk about ordering results for aggregate operations. So we'll talk about how aggregate operations are going to affect result order. And we'll take a look at a bunch of examples, which again is from my EX21 project in the Java 8 folder in the Live Lessons GitHub repository. And after this, we'll take a look and actually run the code. So certain intermediate operations affect the ordering behavior. Not all of them, but some of them do. Here are the ones that do. Sorted, that's pretty obvious. It's going to sort things. So if the input is not already sorted, sorted will affect the output of the stream. Unordered, which is basically a way of saying, hey streams framework, even though the collection here is ordered, I don't care how the results are presented. So I'll run them unordered if you don't mind. And then a couple other ones like skip and limit. And of course, they're just affecting the behavior because they're going to change whether everything comes through or not based on what you're skipping or limiting. So let's take a look at an example. Here, once again, we have a list. And the encounter order is what we had before, 2, 3, 1, 4, 2. We turn that into a parallel stream. It's ordered and non-unique. And then we tell it, be distinct. Now, distinct is an interesting operation. Distinct is a stateful intermediate operation. What that means is it has to collect all the elements that come to it and figure out which ones are duplicates and only allow the ones that are not duplicates to go through. And you can imagine probably does it under the hood using something like a hash set or whatever. I forget exactly what it does. You could look at the code to see what it does. So distinct will get rid of duplicates. So it's kind of as if we turned this arrays list into a hash set first and then ran it through the stream and left out distinct. It's kind of the same basic idea. In fact, like I said, it probably uses hash set under the hood. Now, the other thing we're going to do here is we're going to use limit, which is also a stateful intermediate operation, which is going to limit the output to whatever we set this to. Now, there's not a whole lot of elements in here, so this is probably going to be a small value like 2 or something like that. But what it's going to do is it's going to just let the first 2 elements go through. And again, the results here must be 4 followed by 8, because it's going to preserve encounter order. But this code might actually run a little bit slower than we would otherwise expect because distinct and limit are stateful, and therefore the stream has to break them up. If you recall from our discussions of the internals of parallel streams execution, it has to break it up into multiple phases or multiple substreams, be able to deal with the fact that we've got to look at these things in the right way. And a parallel stream with limit is much more complicated because it's got to keep track of when to stop across the parallel threads. So that gets a little bit tricky. So you would not be surprised if this code would run slower than the code we did before that didn't have distinct and didn't have limit. Now, maybe, if we put unordered here, then this code may run faster because we don't have to worry about the ordering of things. Now, again, the proof is always in the pudding, as they say, or the devil's in the details, or whatever your favorite cliche is. So you'd actually have to benchmark the code to see if it matters at all. It might matter, it might not. Different versions of Java parallel streams might perform differently. Different hardware might cause it to run different. Different implementations of the Java execution environment might affect the behavior. But it might be the case that this will run a little faster because we no longer care about ordering. And in this case, because we've said it's now unordered, the results might be 8 followed by 4, or 4 followed by 8, or whatever. And I guess the other sort of assumption here is that we set limit to be large enough so it gets those 2 values to come through. There's also terminal operations that can affect order. So let's take a look at an example. One that kind of gives it away is the terminal operation forEachOrdered. And you can see here the encounter order is 2, 3, 1, 4, 2. And the list is ordered and non-unique. So that's what we want as the output. So let's see what's going to happen here. So we create ourselves a list, and then we create ourselves a new array list, and we're going to have this list support unsynchronized insertions and removal of elements. Is this going to be a problem? No, and here's why. What we're going to do here is we're going to use forEachOrdered. And forEachOrdered does 2 things. First, it ensures that the output is in the encounter order, even if the intermediate processing in the apply phase is whatever order it happens to be chosen by the fork join pool and the this thread scheduler and the underlying processor cores and so on. But the other thing that forEachOrdered does is it has implicit synchronization. So despite the fact that this results array list is not synchronized, forEachOrdered will make sure there is not problems with race conditions, which is good. However, there's always a cost, there's typically a cost. And the cost here is that this may be a little slower than using forEach because first we have to enforce encounter order, and secondly, we have to do this extra synchronization. I would highly caution not writing code like this. I'm just kind of showing you how it works under the hood. Conversely, if we use forEach instead of this approach with forEachOrdered, then the results don't need to appear in encounter order because of the fact that forEach doesn't preserve encounter order. It could be whatever order it happens to run in. And we use a concurrent linked queue, which does the synchronization implicitly. So it might be the case, maybe, that this approach will be a little faster. And that's because maybe the implementation of concurrent linked queue to add things into a list might be faster than using the synchronization that's used for forEachOrdered. Again, your mileage may vary, so we'll run the code, we'll see what it actually does. Don't be surprised if it behaves differently because different implementations and different environments run differently in different times. Having said all of this stuff, it's almost always a better idea to use a terminal operation that produces a result rather than doing stuff like this. Even if you use a concurrent linked queue, even if you use forEachOrdered, it's still almost always better to use a terminal operation that produces a result because you don't have to do things like remember to initialize these local variables, and all the issues of concurrency are dealt with magically for you because of the fact that these non-concurrent collectors work with parallel or sequential streams. So these are all things that could be cleaned up. And I could also probably replace collect toList with just toList, and it might run even faster, who knows. So that's the overview of aggregate operations and how they affect the ordering of results.